Let's try to get the rest of the class in here. All right, good morning, everybody. I hope the rest of your day yesterday went well and that you are feeling excellent this morning. We're gonna get going in section 8.3 today. That is the last section in chapter 8. It is very similar to what we did last week with the population proportions and estimating those. We're just going to have to slightly change up some of the conditions that we have to check for and the way the formulas are, because obviously we're not dealing with proportions, we're dealing with means, so things change a little bit. But it's a lot of the same logic, a lot of the same types of things we did last week. So we're just kind of building on that and expanding on it. All right, so we have the lesson. I've got a couple extra examples that I want to show you guys after. And a bunch of people just don't want to be in class today. Okay, so we're going to get started, and hopefully the other half of class gets here at some point. So we're going to start with a presentation. You do not need to write absolutely everything down in your notes. From here, there's a few things that you need, like conditions to check for, some formulas that I'll say these ones need to be written down. Other than that, it's a lot of just kind of like information that leads us up to the process that we're going to use. So don't try to like bog yourself down by writing down everything. It's not necessary. So let's get this going. All right, so here we are. We're in chapter 8, estimating with confidence, and today is section 8.3, estimating a population mean. All right. So our objectives today, all right, is to be able to state and check the random 10% and normal large sample conditions for constructing a confidence interval for a population mean. Explain how the t distributions are different from the standard normal distribution and why it is necessary to use a t distribution when calculating a confidence interval for a population mean. Right. Determine critical values for calculating a C% confidence interval for a population mean using a table or technology. Construct and interpret a confidence interval for a population mean. And determine the sample size required to obtain a C% confidence interval for a population mean with a specified margin of error. The last three things, right, in our checking conditions is essentially taking what we did in 8.2 and applying it to means. It's not going to be a lot different. So here we go. So we're going to start by discussing what is the t distribution and how do we get there. So when the sampling distribution of x bar is close to normal, we can find probabilities involving x bar by standardizing. This is what we've done previously. Right, we get z equals x bar minus mu divided by sigma divided by square root of n. And this is like what we saw with our previous sampling distributions. And that takes us from our sampling distribution with an unknown mu to the standard normal curve with the mean of 0, standard deviation of 1. Right? And we can use that to then perform calculations. When we don't know sigma, we can estimate it using the sample standard deviation S sub x. What happens when we standardize? Right, we have x bar minus mu divided by S sub x divided by square root of n. What do we get? When we standardize based on the sample standard deviation S sub x, our statistic has a new distribution called a t distribution. It has a different shape than the standard normal curve. It is symmetric with a single peak at 0. However, it has much more area in the tails. This is what it looks like. And you don't necessarily need to write down the formula for the t-distribution. We're not necessarily going to use that specific formula, at least not in this section. And we have this from previous sections, the z-score, the standardizing. Right. So again, here's our example. The t-distribution looks a lot more spread out, a little shorter, a little wider. The standardized score, right, is a little taller, but a lot more narrow. And it's kind of what we would expect. Once you get beyond 2 standard deviations from the mean of 0, everything's pretty small at the tails. Like any standardized statistic, t tells us how far x bar is from its mean mu in standard deviation units. So very similar to what we did with the proportions, population proportions, and we found the critical value. We use z star to represent that critical value because it's a value of z from our standard normal curve. We're now going to use t star as a critical value based on the t value from our t distribution. Right. There's a different t distribution for each sample size, specified by its degrees of freedom, notated as df. Right. So the t distributions in degrees of freedom. When we perform inference about a population mean mu using a t distribution, the appropriate degrees of freedom are found by subtracting 1 from the sample size n, making df equal to n minus 1. The degrees of freedom is a number that we look up on the t distribution table, which is table B. Let me pull it up for you guys so you can see what it looks like. And we'll see this later today as well. So this is what table B looks like. It is a 1-page table. It's not 2 pages like table A. And you see over here, we have the DF, degrees of freedom. It goes from 1, it hits every number from 1 to 30, and then it starts skipping. It's not a mistake. It's not like in table B, we don't have those numbers in between, and I'll explain how we use this shortly. We see an example. Right, and then we have confidence levels down across the bottom. Tail probability P is listed across the top here. And that goes back to this picture. The tail probability tells us the proportion, right, greater than that T value. So again, we will write the t distribution with n minus 1 degrees of freedom as t sub n minus 1. And we have conditions for constructing a confidence interval about a, assuming they meant to write mean here. Draw an SRS of size n from a large population that has a normal distribution with mean mu and standard deviation sigma. The statistic t equals x bar minus mu divided by s sub x divided by square root of n has the t distribution with degrees of freedom df equals n minus 1. When the population distribution isn't normal, this statistic will have approximately a t n minus 1 distribution if the sample size is large enough. Right. So again, similar to what we've seen in the past, as we get larger sample size, things tend to turn more normal. Right. And in this case, as our sample size gets larger, the symmetric distribution, the t distribution, works, even if our parent, the original population was skewed. Right. Again, you don't need to write this part down. This is just kind of moving us towards where we're going here. So, anyone have any questions so far? Anything I can clarify? So when comparing the density curves of the standard normal distribution and t-distribution, several facts are apparent. The density curves of the t-distributions are similar in shape to the standard normal curve, right? We have the standard normal curve here as the tallest and most narrow curve on this page here. Right? And the other two curves are t-distributions, one with 2 degrees of freedom, one with 9 degrees of freedom. The spread of the t-distributions is a bit greater than that of the standard normal distribution, right? They're wider, so they're more spread out. And the t-distributions have more probability in the tails and less in the center than does the standard normal. Right? In other words, that's why the tails are farther away from the horizontal axis. There's more area underneath them. As the degrees of freedom increase, the t density curve approaches the standard normal curve ever more closely. And this makes sense based on what we've learned previously, in that as we do larger sample sizes, our variance gets smaller, which means we get closer to this standard normal. Does anyone need a moment to write anything down? So then let's look at an example of how to use table B to find critical T star values. So our problem is, what critical value T star from table B should be used in constructing a confidence interval for the population mean in each of the following settings. Right. We have a 95% confidence interval based on an SRS of size n equals 12. In table B, we consult the row corresponding to degrees of freedom equaling 12 minus 1 equals 11. So in our table here, we'll find 11 under the DF column. We'll go to the 95% confidence level across the bottom and find their intersection. We get 2.201. And that's what this is saying to do here. So the desired critical value is T star equals 2.201. And this critical value is used very similarly to how we use the critical value with proportions, whatever statistic plus or minus critical value times the standard deviation of the statistic or the standard error. Another example, a 90% confidence interval from a random sample of 48 observations. So with 48 observations, we want to find the T star critical value for DF equaling 48 minus 1 equals 47 and 90% confidence. So what we'll notice here, there is no DF equaling 47 in table B. So we use the more conservative DF equals 40. Think of it as Price is Right rules. You want to get as close as you can without going over. So even though 50 is closer to 47, it would be an overestimate. Right? So we're going to go more conservative and at least be more confident about what we're finding and use 40. We don't want to go over. So the corresponding critical value is T star equals 1.684. Right, the one that goes with 40 here. Is there any questions about how to use table B here for these examples? And table B will be included in the formulas, tables and formulas that you're provided on the AP exam. You just need to know how to use it. Okay. So we similarly to having conditions with proportions, we have conditions for estimating mu. So our conditions for constructing a confidence interval about a mean, and these you're probably going to want to write down. We need to make sure that it is random, same as with a proportion. The data came from a well-designed random sample or randomized experiment. We need to check the 10% rule when sampling without replacement, and check that n is less than or equal to 1 over 10 times n, where little n is our sample size, big N is the population size. And then we have the normal/large sample. The population has a normal distribution, or the sample size is large. Those are the things we're checking for. If the population is normally distributed, then we know that the sample will also be normally distributed. If the population distribution has unknown shape and n is less than 30, we need to use a graph of the sample data to assess the normality of the population. Do not use t-procedures if the graph shows strong skewness or outliers. Right, so when we check this, if the population is normally distributed, sample's good to go with normal distribution. We can use these t calculations and such. Or the sample size is large enough, greater than or equal to 30, same as the central limit theorem that we saw in our previous chapter. Right? If those things are not satisfied, right, and our sample size is less than 30, we have to graph the data. Right? We need to make a box plot, we need to make a dot plot, something to see the distribution of the data. If it is strongly skewed or if there's some crazy outliers, we cannot continue. Right? Now, I've been told that as far as AP is concerned, they will not try to trick you with this. If the population or the sample size is less than 30 and the population is not normally distributed, and you have to graph this, it will be very apparent that the graph is very skewed or that there's some crazy outliers. They're not going to have it be a judgment call. It should be incredibly apparent. See, we need a moment to write anything down. Please raise your hand. Okay. So now we'll do constructing a confidence interval for mu. Right. When the conditions for inference are satisfied, random 10%, normal large sample. The sampling distribution for X bar has roughly a normal distribution. Because we don't know sigma, we estimate it by the sample standard deviation S sub X. So the standard error of the sample mean X bar is S sub X divided by square root of n, where S sub X is the sample standard deviation. It describes how far X bar will be from mu on average in repeated SRSs of size n. To construct a confidence interval for mu, we replace the standard deviation of X bar by its standard error in the formula for the one sample Z interval for population mean. Use the critical values from the t distribution with n minus 1 degrees of freedom in place of the z critical values. And that is, we use this formula. Right, statistic plus or minus critical value times the standard deviation of a statistic, and we get X bar plus or minus T star times the standard error S sub X divided by square root of n. So this is kind of like the population mean version of what we did for population proportions. Right? We had P hat plus or minus Z star times the square root of P hat times 1 minus P hat divided by n. Right? This is the companion formula, if you will. Right? And so that leads us to the next thing. Right? The one sample t interval for a population mean. This is our inference method for estimating a population mean. Right? The one sample t interval for population mean is similar in both reasoning and computational detail to the one sample z interval for population proportion, which is what we did in section 8.2 to make an inference about a population proportion. So we have the one sample t interval for population mean. You're going to want to write this down in your notes somewhere. When the conditions are met, A C% confidence interval for the unknown mean mu is x bar plus or minus t star times s sub x divided by square root of n, where t star is the critical value for the t n minus 1 distribution. All right, so this goes back to our degrees of freedom on our table B distribution, with C% of its area between negative t star and t star. This is the formula we will use to create our confidence interval. If you need a moment to write this down, can you please raise your hand? Okay. The example. Let's see how to use this one sample t interval for mu. Environmentalists, government officials, and vehicle manufacturers are all interested in studying the auto exhaust emissions produced by motor vehicles. The major pollutants in auto exhaust from gasoline engines are hydrocarbons, carbon monoxide, and nitrogen oxides, or NOx. Researchers collected data on the NOx levels in grams per mile for a random sample of 40 light-duty engines of the same type. The mean NOx reading was 1.2675. The standard deviation was 0.3332. We want to construct and interpret a 95% confidence interval for the mean amount of NOx emitted by light-duty engines of this type. All right. So we want to estimate the true mean amount mu of NOx emitted by all light-duty engines of this type at a 95% confidence level. Right, this is following our 4-step process for estimating with confidence. Now we're going to state, plan, do, and conclude. So this is what we're doing. We're just giving a statement. This is what we're going to do. We now plan. If the conditions are met, we should use a 1 sample t interval to estimate mu. Part of the planning process here is checking our conditions. Right? Random. The data came from a random sample of 40 engines from the population of all light-duty engines of this type, so it is random. The 10% condition, we are sampling without replacement, so we need to assume that there are at least 10 times 40 or 400 light-duty engines of this type in the population. That seems fair. And large sample, we don't know if the population distribution of NOx emissions is normal. Because the sample size is large, n equals 40 is greater than 30, we should be safe using a t distribution. So we have now checked our conditions. We're clear to move forward and do some calculations. From the information given, x bar equals 1.2675 grams per mile, and S sub x equals 0.3332 grams per mile, or the standard deviation of the sample. To find the critical value t star, we use the distribution with degrees of freedom 40 minus 1 equals 39. But again, there is no row corresponding to 39 degrees of freedom on table B. We can't pretend we have a larger sample size than we actually do. So we use the more conservative degrees of freedom equals 30. Again, we're playing by Price is Right rules. You want to get as close as you can without going over, which means we cannot use 40. We go back down to 30. That gives us this 2.042 as our t star value. Does anyone have any questions so far? So we use our formula here, x bar plus or minus t star times s sub x divided by square root of n. That sets up to this 1.2675 plus or minus 2.042 t star. times 0.0 or 0.3332 divided by square root of 40, and we get 1.2675 plus or minus 0.1076 for the interval from 1.1599 to 1.3751. Which means we're now to our conclusion. We are 95% confident that the interval from 1.1599 to 1.3751 grams per mile captures the true mean level of nitrogen oxides emitted by this type of light-duty engine. Right. Is there anything I can clarify on this example? So just like with proportions, we sometimes need to choose our sample size ahead of time. Right? We determine a sample size for a desired margin of error when estimating a mean, and much the same way we did when estimating a proportion. Right? To determine the sample size n that will yield a level C confidence interval for a population mean with a specified margin of error ME, we need to get a reasonable value for the population standard deviation sigma from an earlier or pilot study. That's the only option for guessing sigma. Right? With proportions, we had two options. We could use results from an earlier or pilot study, or we could use 0.5 as the guess. In this case, if we don't have earlier or pilot studies to go off of, we got nothing. Right? We'll find the critical value Z star from a standard normal curve for confidence level C. So if we're choosing the sample size, we're now moving back to using table A. Right. We're going to set the expression for the margin of error to be less than or equal to ME and solve for N. Right. Similar strategy as we did with proportions, just get a little bit of a smaller formula. Right. So I need a moment to write this down. So we'll look at an example here. Researchers would like to estimate the mean cholesterol level mu of a particular variety of monkey that is often used in laboratory experiments. They would like their estimate to be within 1 milligram per deciliter, mg per dl, of the true value mu at a 95% confidence level. A previous study involving this variety of monkeys suggests that the standard deviation of cholesterol level is about 5 milligrams per deciliter. Our problem is obtaining monkeys is time-consuming and expensive, so the researchers want to know the minimum number of monkeys they will need to generate a satisfactory estimate. So we're at a 95% confidence level. Excuse me. That translates to a Z star of 1.96 using table A. We're going to use sigma equaling 5 as our best guess for the standard deviation of the monkey's cholesterol level. We're going to set the expression for the margin of error to be at most 1 and solve for n. That looks like this. We get 1.96 times 5 divided by the square root of n is less than or equal to 1. We multiply each side by square root of n and divide each side by 1. And we get 1.96 times 5 divided by 1 is less than or equal to square root of n. We square both sides. We get 96.04 is less than or equal to n. Because 96 monkeys would give a slightly larger margin of error than desired, the researchers would need 97 monkeys to estimate the cholesterol levels to their satisfaction. And again, this goes back to the inequality here. N must be greater than or equal to 96.04. 96 is not greater than or equal to 96.04, so we have to round up. Is there any questions about this example? Ready. So then that gets us to the end of this presentation. And we're going to look at a couple other examples that I have already. in OneNote. All right, so we've got our examples here. Move stuff out of the way. So we have a bone loss by nursing mothers. Breastfeeding mothers secrete calcium into their milk. Some of the calcium may come from their bones, so mothers may lose bone mineral. Researchers measured the percent change in bone mineral content, BMC, of the spines of 47 randomly selected mothers. Okay. During 3 months of breastfeeding, the mean change in BMC was negative 3.587%. And the standard deviation was 2.506%. Okay, so this was X bar, and this is our S sub X. Okay, we need to construct and interpret a 99% confidence interval to estimate the mean percent change in BMC in the population. Okay, so we're going to need that. And we're going to go through this using our 4-step process. Right, so step 1, we need to state what we're going to do. We want to estimate mu, the true mean percent change in BMC in the population. All right, so that's what we're going to do. And we'll go to plan. Right, that's step 2. We have if conditions are met. We will use the 1 sample T interval for mu. Right, this will be our inference method. So now we need to check, are all of our conditions satisfied? Right, random. All right, we have 47 mothers were randomly selected. So that condition is met. We are sampling without replacement, so we have to check our 10% condition. And essentially we assume that 47 is less than 10% of the population of all breastfeeding mothers. This is a fair assumption to make because we can assume in the population, like just in the US, there's going to be more than 470 mothers who are breastfeeding. at any given time. And then we have our normal large sample condition. Since n equals 47 is greater than 30, the sample is large enough. So we can use our t distribution. So we've checked our conditions, right? We're done with the plan phase. Right, so now we move on to creating just a touch more space, the do phase. Right, and now this is where we'll use table B. Let's kind of get our data together. Right, we have n equals 47. Right, so our degrees of freedom equals 47 minus 1. It's 46. We'll need x bar was equal to negative 3.587. Right, and our sample standard deviation was equal to 2.506. So what we need now is t star. We don't have that. That's the last value we need to get our interval. So we have our degrees of freedom here. We need to find that on table B. So we're going to look into table B here. And again, notice 46 is not on table B, and we can't go over 46. Right, so we're going to have to use 40. Right, so we're going to just go through and highlight all of this row, show it all. And we want a 99% confidence interval. So we go across the bottom here and we find 99%. Right, that's going to be right there towards the bottom. And we then go up here. And we get the intersection of those two, right? The row and the column of 2.704, which means t star is the value 2.704. So we'll go back up here and calculate our interval. And that's going to be negative 3.587 plus or minus 2.704 times 2.506 divided by square root of 47. Right. And this is using the formula, right, x bar plus or minus t star times s sub x over square root of n. Right, and we'll finish our calculation here. When we do this, right, put this through our calculator, we get the interval negative 4.575 to negative 2.599. Right. And so this is our interval, right? It's our 99% confidence interval. So any questions about the math or the process that I've just shown so far? Got one more step in our 4-step process, but is there anything I can clarify? Okay. So we're going to go down to the bottom here and write our conclusion as the last step of our 4-step process. Right. And for that, we say we are 99% confident that the interval from negative 4.575 to negative 2.599 captures the true mean percent change in BMC for breastfeeding mothers. And now we've answered the question completely. Okay. And I want you guys to consider this is something that's going to start being stressed, is using this 4-step process to outline your solutions. That's going to become important. It guarantees that you're not going to miss things. Right? And then part B here, right? Based on your interval from part A, do these data give good evidence that on the average, nursing mothers lose bone mineral? Explain. Right. So here's our answer. Since all the plausible values are negative, right, indicating bone loss, the data give convincing evidence that breastfeeding mothers lose bone mineral on average. Okay. And so now we're able to use our interval, the work that we did, to support a claim. We could also use the contrary to like counter a claim if needed. Is there anything I can clarify from that first example? All right. So now we'll move on to the next example here, the SAT. High school students who take the SAT exam a second time generally score higher than on their first try. Past data suggests that the score increase has a standard deviation of about 50 points. That number we're going to need. How large a sample of high school students would be needed to estimate the mean change in SAT score within 2 points with 95% confidence. Show your work. All right, so this is choosing the sample size. And again, I'm just going to start by writing down what we know. We have a standard deviation to use. Right, sigma is 50 points. We have a margin of error that we're targeting, 2 points. We have a 95% confidence interval. Which implies a z-star that we will use of 1.96. And that's again from table A. And so we're trying to find n. And we'll use the rule, or the formula, inequality, technically, of z-star times sigma over square root of n is less than or equal to the margin of error. And we'll solve for n. So we replace our variables with the known values. We have 1.96. Right? Sigma is 50 divided by the square root of n. It's less than or equal to 2. We're going to do some rearranging. We're going to multiply each side by the square root of n and divide each side by the divide each side by 2. So we get square root of n divided by 2, square root of n over 2. The square root of n is canceled from the left-hand side. The 2 is canceled from the right-hand side. And we get 1.96 times 50 divided by 2 is less than or equal to the square root of n. We're going to square each side. The squaring cancels our square root of n. Right. And we end up with 2,401 is less than or equal to n. Right. And we can conclude that we would need at least 2,401 high school students in our sample to estimate the mean change in SAT score to within 2 points with 95% confidence. Right. And so that's an example of how to choose the sample size. What questions do you have? What can I clarify? All right, so these examples will get posted onto Canvas shortly, along with video and everything of today's lesson. The practice problems for section 8.3 and their solutions are ready to go in Canvas in the resources for chapter 8. And the assessments, multiple choice and free response questions should be ready shortly. I believe I just posted the multiple choice one for chapter 8. Please don't feel like you need to start that right now. You shouldn't wait till later on in the week after we've done our example, like more practice problems and such tomorrow. But those will be ready this week. And as we've been doing, tomorrow we will have more practice opportunities. I don't know if I'm going to do Desmos or Pear Deck. I haven't decided yet, but one of those two things to give you guys some practice. And other than that, if you have any other questions, you need support or anything, help with previous lessons, previous assessments, please stick around, let me know, or send me a message. And I will see you tomorrow for more practice on estimating a population mean. Have an awesome rest of your day.